Hello everyone, I am Atul from Carnegie Mellon, and I am here to present my work OwL, which is accurate LoRa localization using TV whitespaces. This work was done jointly with Akshay, Vaibhav, Anthony, Bob, and Swarun. Future smart city applications would be powered by multiple IoT devices installed at different parts of the city, with each device transmitting messages few times a day. One of the key technologies which can enable such smart city applications is LoRa. LoRa works in 902 to 928 MHz ISM band on a 125 kHz bandwidth, provides a range of few kilometers, and can remain functional for up to 5 to 10 years. Apart from its long-range communication capabilities, LoRa was also designed for its geolocation capabilities. This can enable applications such as infrastructure monitoring, inventory management, and wildlife tracking. The problem of localization is not new, and there has been tons of research work already done in this field. Typically, we look for three things in a localization system for IoT devices. It should work at low power, it should be accurate, and it must work at long ranges. If we compare the existing localization technologies, we find that GPS can work at large ranges and is very accurate, but is not low power. Many low power solutions, such as Wi-Fi based Chronos, Bluetooth based Alps, and backscatter systems, such as MuLocate, can almost provide centimeter level accuracy, but they are range limited to few tens of meters, rendering them unsuitable for long range localization purposes. Other LoRa-based solutions, such as Satellog, are low-powered and work at long ranges, but perform very poorly in their accuracy. Thus, there is a gap in literature for a solution which is accurate, has long range, and can perform localization at really low power. Is there any technology by which we can get all the three benefits? We believe LoRa has the capability to provide these benefits. We present OwL, a LoRa-based LPWAN localization system which achieves high accuracy by frequency hopping across TV whitespaces. It conserves battery life by achieving high accuracy while only hopping few number of frequencies via a smart frequency hopping algorithm. We observe an overall median error of 9 meters across both line of sight and non-line of sight environments. Before we deep dive into the system, let us understand how do we perform localization of LoRa devices. Suppose we are given a client device at an unknown location and multiple base stations distributed geographically at known locations. To localize this client device, we just need to know these distances D1, D2, and D3 to the base station. And we can trilaterate these distances to pinpoint the exact location. To get this distance, we measure the time of flight of the LoRa signal to the base station. Multiplying time of flight with the speed of light will spit out the distance of the client to the base station. To find this time of flight value, we use a technique called frequency hopping. The LoRa client sends a signal at a particular frequency f1, and the base station measures the phase of the wireless channel received at that frequency. This is repeated across several frequencies one by one, and we get a set of corresponding channel phase information at these frequencies. Assuming that we only have the direct path signal from the client to the base station, these phase values are related to the time of flight of the direct path as 2 pi f into tau modulo 2 pi, where tau is the time of flight. However, one important thing to note here is that the accuracy in measuring the time of flight heavily depends on the bandwidth, that is, the effective span of the frequencies which these individual frequencies can cover. This would be fn minus f1 in this case if these frequencies are sorted in the ascending order. So let's look at the bandwidth which is available to us. As I already mentioned, LoRa as a standard works in ISM band on a 125 kHz bandwidth. However, few years ago, FCC announced new TV whitespace bands for use by unlicensed users. But they can only use it if they do not interfere with the already present users in the spectrum. Also, There exists off-the-shelf LoRa radios which can operate on this TV whitespace band. Thus, there lies an opportunity to exploit these whitespaces and increase the accuracy. A naive approach could be to hop at all the available frequencies from 400 MHz to 928 MHz to get as much information as possible. However, doing that in the LoRa setting is not feasible. The reason is very simple: low bandwidth of a single LoRa packet. As shown in the figure, we have almost 350 to 400 MHz of available bandwidth. Hopping across all frequencies with a 125 kHz packet would result in more than 3000 frequencies, which amounts to almost an hour of transmit time for a single localization. This will use up almost 3% of the total battery life and completely drain the battery of the IoT device in just 16 days, assuming that we perform localization twice a day. This means that we need to be smart when we are choosing frequencies to hop, so that we get the maximum information about the direct path from the base station to the client. So how do we hop frequencies? We design an algorithm which works in two steps. In the first step, we choose some initial frequencies, and in the second step, we use these initial frequencies in an iterative manner to select a new frequency. So let's talk about the first step of the algorithm, that is choosing initial frequencies. Here we explore three different approaches. For the first case, we uniformly sampled some fixed percentage of frequencies across the whole bandwidth. This approach has the potential to cause aliasing, particularly for the case of large time of flight value. This happens because of the 2π phase wraparound, leading to ambiguous time of flight estimates. Thus, we inferred that some of the frequencies chosen should be very close together to avoid this issue. For the second case, we sample fixed percentage of frequencies randomly across the given bandwidth. This approach can lead to poor resolution of the time of flight values in cases where the equivalent bandwidth is smaller than the whole band. Thus, we inferred that the frequencies chosen should be spread out across the whole bandwidth. The approach which we used in our system ensures that most of the frequencies we choose are close together to avoid aliasing and also span the whole available bandwidth to get good resolution. This graph shows the effect of how the initial frequencies can affect the time of flight estimation. We observe that our approach performs much better than uniform and randomly sampled approaches when the number of chosen frequencies is low. This is good, as we want less number of frequencies to be chosen initially so that we can choose remaining frequencies using our iterative frequency hopping algorithm. Coming to the second step, how do we iteratively choose the next frequency? Given you have channel information at some initial frequencies, we first calculate the time of flight profile. Consider this time of flight profile as an estimated environmental model which represents the energy of all the time of flights possible. There are multiple time of flights in this profile because of the presence of multipath in the environment. Now, after getting this environmental model, we use it to decide which frequency is the best frequency to hop onto. For that, we first estimate the channel at all the new candidate frequencies using this model. Now we calculate multiple time of flight profiles, with each profile created by the combination of the already seen frequencies and a new candidate frequency. Each one of these new time of flight profiles is compared with the old time of flight profile. The candidate frequency, which reinforces the existing time of flight profile to the maximum extent, is chosen to be the new frequency to hop to. Mathematically, it boils down to the candidate frequency, which has the maximum energy in its profile. After getting the new hop frequency, the base station asks the client to hop at the new frequency, and after getting this response, updates the existing time of flight profile to create a new profile. This loop is repeated until your battery life allows for, at which the base station can terminate the algorithm. At the end, the time of flight value with the maximum power is chosen to be the time of flight from the direct path. Finally, the localization is performed by trilating all the TOF values obtained across base stations. We also take advantage of the geometric constraints of the environment and a particle filter-based sampling approach to speed up the localization process at the base station. There are many other challenges which we address in our paper. Some of them are, first, how do you measure the correct phase value at low SNR values? Second, what are the TV whitespace related considerations we had to think about? And third, how do you synchronize both clients and base stations together to estimate accurate phase, which is devoid of any clock related impairments? To resolve this, we calculate time difference of arrival in place of time of flight. Time difference of arrival refers to the difference of time of flights to the two base stations, thus removing any client phase offsets in the received signal. However, even if we use time difference of arrival, the concepts explained in the talk remains the same. More details about how we address these challenges can be found in the paper. To implement our system, we use Semtech SX1262 radios as our LoRa clients, USRP's N210s as our LoRa base stations, and Nikon laser rangefinder for our ground truth. We deploy our system at CMU campus with 4 base stations and 50 different client locations. This plot represents the CDF of the time difference of arrival accuracy. We compare the time difference of arrival accuracy against the time difference of arrival accuracy of the baseline localization system, which uses pure RSSI values along with the log normal path loss model to perform localization. We achieve 3.6 meters median error in line of sight situations and 14.8 meters error in non-line of sight situations. This is a significant improvement over the baseline, which has a median error of 90 meters. This plot represents the localization accuracy of our system compared against the same baseline. We observe that we obtain 3.9 meters median error in line of sight situations and 15.7 meters in non-line of sight situations, which is an overall of 9 meters of median error. This is a significant improvement over the baseline median error of 53.6 meters. However, our non-line of sight error is still a bit high due to the extreme multipath scenarios where our system fails. There are various other results that we showed in our paper, such as how resilient our enhanced phase estimation method is, what are the trade-offs between the localization accuracy and the battery life, and how does multipath impact the localization accuracy. You can read more about it in the paper. Our system does have some limitations. It is not designed for moving objects, as it needs to remain static for the time it is frequency hopping. The evaluation of our system only measures the 2D location due to the lack of access to the building roofs due to COVID. Also, our system suffers under the extreme occlusion cases, such as in deep indoor environments or in basements. To conclude, OwL is a LoRa-based LPWAN localization system which achieves high accuracy by frequency hopping across TV whitespaces. It conserves battery life by only hopping few number of frequencies in a smart fashion. And it provides an overall median accuracy of 9 meters across both line of sight and non-line of sight scenarios. You can find more about our paper at the below link. Thank you, and I'm happy to take any questions.